informal. Actually, I request you to come forward and structure this. So we had 3 interesting talks this morning, and there were questions asked, and then I had noted down some questions. I'm sure many of you still have some of those questions fresh in your mind. So I thought we could start with those questions and then slowly go forward. Now, one of the things that happened during tea break and lunch break was that people wanted some concrete MIJ. Like, is there a simple model where you can either numerically get this matrix and see it and then get a feel for it? Like I was asking in the last question, then Ramsesha was saying that it's a sparse matrix, doesn't tell much about itself. But I know that people have tried to rewrite some well-known strongly correlated wave function in terms of tensor product states. There, of course, some of these things are there analytically. I haven't had time to get them. So that is definitely one question to ask. To get a feel for these matrices as calculated by Dmrg. For simple models like Ising model in transverse field in one dimension, which is exactly solvable, or Heisenberg Hamilton, which is also exactly solvable with the answers. Not that user-friendly method. So this is one thing. And then there were specific questions which Vijay and I raised during Miles' talk, going back and forth with Psi 3, some block in between. And there seemed to be some connection between what Ramsesha said and that. So I thought it's a good thing to connect Ramsesha and Vijay and I. So that at some point what I will do is I will go back and show Miles' presentation and go to that section. And you can raise that question again. And we can see it in the light of what Ramsesha said. So this is roughly what we will structure, we do today. Tomorrow afternoon, of course, we have better things to do in the seashore, watching the sea and so on, apart from listening to talks. Then the day after tomorrow, we will have a formal discussion between this MERA and ADSF correspondence. We are trying to get some string theory colleagues to come and discuss about it. So Srikinder will be on the other side. So for today, and also I would like to invite suggestions from you and also questions from you. If you have any particular suggestion how to go about doing these things, it will be very nice. So Amit, you had a suggestion.
I was just mentioning that there are transversalizing models which has these interaction. I'm audible, I'm sure. Don't have to.
No, formality.
Okay, the transversalizing model with 3-spin interaction.
With 3-spin interaction.
Which makes product ground state. People have calculated the fidelity and other quantities using this matrix product nature of the ground state. But I don't remember the details. I can tell tomorrow.
That would be nice. So you can.
And second thing, there was some comments on the connection to conformal field theory at the quantum critical point.
Yes.
There I remember there is a paper by Shubroto of IISc and Frank Coleman and others who looked at the transversalizing quantum critical point and tried to numerically simulate using a matrix product state. And they calculate what error you make, and that error scales with the size of the matrix dimension. These are the 2 points I just wanted to mention. Maybe I can tell you.
Theories and calculated various scaling exponents that you need using tensor product representation. So it exists in the literature. I'm not familiar with it. So Nandini, why don't you say what you were telling me this afternoon? But you wanted something concrete, right? Some example would have been. So Srikinder, you were saying that you could do something about matrix product state and then some time evolved.
Okay, so what I was just mentioning was that it's usually instructive to write down the code for at least one of these algorithms yourself, and rather than wanting to see something in the matrix elements itself, that helps clarify a lot of things. And I was just suggesting that, for example, imaginary time evolution with the MPS, you can write this code within half an hour and already run and see what happens with the Ising model. And if
So like Miles was telling in this website, items.
yeah, I'm not familiar with that. So they've probably done this recently, but this can be, it's quite.
Wonderful, wonderful. So here is a volunteer, Rajiv Singh, and so can you do it now?
Yeah, if the limits work on that, I can do it.
Yeah, this has website.
But no, limits are password protected there.
Oh, so we can ask number. So this is, you will demonstrate.
See, I don't know much of the technique, but I'll show how the code, what the code is. It's a short code. You can try to figure out what every various commands mean, and what it is actually simulating. I'll show what it is.
And will it solve a simple problem?
Yeah, I don't know what problem it is solving.
Will give you.
Yeah, you can tell us the answer. Question: what is the problem?
Yeah, good. Let me see. Yeah.
So here there is a, if you click on learn, there are a bunch of things, and then if you go to code recipes, there is a small code here, perform a Dmrg calculation. So there is some explanation here. Well, let me just try to read it. To do any Dmrg calculation, you first need a Hamiltonian. The simplest way to obtain one is to use a predefined Hamiltonian provided with the library. The site indices included in the Hamiltonian are provided by a model object. So this is one, spin 1 model n. I don't know what that means.
N is number of sites.
N might mean number of sites, and it's a what, spin 1? I don't know.
Spin 1 Heisenberg model.
Okay, and the next line says it's a Heisenberg model.
Oh, wonderful. So he will demonstrate. Good. Great.
Okay.
Read. You are teaching us. So here we have.
Okay, here we have chosen to use spin 1 sites, and our lattice size is n. Spin 1 sites. So every the spin is 1. Instead of spin half, it is spin 1. Okay. Next we
That, just for the sake of students, spin 1 as opposed to spin half with nearest neighbor coupling leads to a gapless situation.
okay,
Whereas spin half always leads to
gapless.
gapless situation. This is called Haldane gap phenomenon.
Okay.
So it's easily addressed using Dmrg.
Okay. So next we instant. Let me just check if this is the example I used. Just a minute. No, I don't think so. Let me just check one thing. Okay, this is the example. So because here the whole code is there, so I didn't have time to go through everything. So I will just run this code.
Please go read through whatever you read.
The previous one,
Yeah.
but the code is not there, so I will not able to show anything. So I will try to do this one. It says measure the properties of an MPS wave function. Here how to measure some properties of the Heisenberg model wave function by adding to the code from the previous example. Okay, so the one which you are looking just now, I think that code will be extended, so we can actually go through that. Okay, so here we were looking at spin 1 n site model where each site has spin 1, and then this line NPOH is equal to Heisenberg model starts the Heisenberg model. So this is C++ code. Then we say before beginning a calculation, we need to specify how many Dmrg sweeps to do, and what schedule we would like for the parameters controlling the accuracy. These parameters are stored within a sweep object. So this is the way. So this is the way to define it. Then set number of sweeps is 5. 5 sweeps will be done, and maximum m is 100. So m, the parameter of Dmrg, I think, the dimension which we keep, and the cutoff is 10 to minus 5. Sorry. I don't know. I don't know. It might be accuracy or something. I have no idea.
The point is that I think when some accuracy is 10 to minus 5, it stops recording.
Yeah. Okay. The argument sweep expm is the first in the first line tells the sweep object to exponentially increase the maximum number of states kept in each sweep until it reaches a maximum which is 100 here. So it will actually so it will start. I think it will start with some small value of m, and if the cutoff is reached with a lesser value of m, it will take that value, but it can go up to 100. The maximum m which is allowed is 100. Okay. The wave function must use the same sites as the Hamiltonian. So we construct it using the same model. Okay, this is some so this is some technicality. This is the definition of wave function, MPS psi bracket model. So we are declaring the MPS state. By default, an MPS is initialized to a random product state. We could also set psi to some specific initial state in order to accelerate the Dmrg convergence time. Okay. Finally, we are ready to call the Dmrg, and this is the line which will call the Dmrg. Real energy is equal to Dmrg. Psi is our trial wave function, which by default will be a random product state. H is the Hamiltonian, which is Heisenberg Hamiltonian here, this line, MPO H is equal to Heisenberg model, and sweeps takes care of all these things, that 5 sweeps will be done and 100 will be the maximum number and all those things. And yeah, so this is this. And now what we are so that line will do the Dmrg function call, will actually run the simulation. And then what we are saying, so here we learn how to measure some of the properties of the Heisenberg model wave function by adding to the code from previous examples. So that's what we are looking at right now. Essentially, we need three pieces to take an expectation value of some property. The operator. Sorry. Yes.
I just want to get some conceptual clarity. So
Yeah.
I think where Ramsesha had done this finite size Dmrg, right?
Yeah.
So he did this infinite system Dmrg, had n by 2, and then so I think this code starts at that point in the sense that it sets up this trial density matrix somehow using some trial matrix.
So yeah, see, trial is it starts with a random product state as the trial.
It's going to do the shifting, zipping, and then zipping back. So it's not constructing the n by 2 density matrix, trial density matrix from the infinite size. Yes, so the finite size.
So yeah, so for example, consider trying to measure the z component of spin on some site j of the Heisenberg chain. This operator is a method. This thing. So what we are saying, we just say so in this line we are saying we will measure the sz at site j. Okay. Likewise, there are operators for the site j spin raising s plus and lowering s minus method. Okay, so this line is actually implicitly built in the library. The next line, there is an efficient way to take the inner product of these local operators with MPS wave function. To do this, we must first call the function psi position j. This step is absolutely vital. It tells the MPS wave function to put all the information about the amplitude of the various spin occupations into the site j. Without this step, we would not be okay. So see, right in the morning we saw that we can, if we have to make a measurement at a given site, we can actually contract everything else. That's what this line will actually achieve. It will say that the site j will be measured, so to try to take care of the wave function accordingly. Well, I don't know. Well, after calling psi position j, all the psi dot AA. Yeah, this one has to understand the library more. I don't know what this means. Tensors for n not equal to 0 form the basis weighed by the wave function amplitude. As basis tensors, these psi dot AA do not have amplitude information. Only the psi dot AA does.
Sorry, SE execute some specific trial initial state and look at the.
See the in the so this is the entire code actually here. So forget the first few lines. So if you look here, that is the number of sites, this is the number of sweeps. We will start with, if m, the parameter will start with value 1 and the maximum it will take is 100. So this we were explaining, he was explaining earlier also, and this is some cutoff. This we are declaring that we will use a spin 1 model of with n sites, and the model is a Heisenberg model, and this is the initial state. What is happening here is see, I think we are putting okay, so yeah, what is happening here is odd sites are set to up and even sites are set to down in this line. I mod 2 is equal to 1. If this statement is true, if this statement will be true for I odd. If this is true, this line will be executed, which will put the ith spin to up. If it is false, which will happen for I even, it will put those spin to down. So we are using a state with up down, that is the initial state. Yeah. Then so that was that. So then we are this line declares the wave function MPS state. So psi model. So model is our end state model, and initial state we have declared like this, the up down state. So that this line will start that. Then there's some output. Then see, this line was present before. So here what we are saying is so we have
Question for clarification.
yes,
Suppose you start with this up down,
yeah.
It's a very simple factorizer state. Can it return like a matrix product state
I don't know.
involving? That's all, just can you put one? I see, then you enlarge as you
So okay, so in this line we set up the sweep parameters where we will start with m equal to 1, maximum value will be
what is chi? What that's I see.
yeah. And this line will perform the the Dmrg calculation, and En most probably will store the ground state energy, which we will print out in the next line. Now next part of the code is actually going to measure the spin. So this line Sj dot Sj plus 1 by means of S plus and S minus.
So then basically it is taking SZ, SZ, SJZ plus 1 half of SZ plus S minus.
Yeah.
So then SI minus SJ plus 2.
Yes. And okay. So yeah. So never mind the next few lines. Now what we are doing here, so this is a way to put a for loop in C, C++, etc. So we will go, J will take value from 1 to n, so we will go on every site, and we will say that, so psi was our wave function, this tensor product state. We will set the position equal to J, so we will make the measurement at the jth position for each value of, for every site. That's what we are going to do here. So what we are saying here, move psi to get ready to measure at position J, this is the line. After calling this returns a local representation of the wave function, which is the proper way to make measurements. So as soon as we call this thing, it will do the contraction on the two sides of the site J, and so next time when we try to calculate something, it will do it very efficiently. If this line is forgotten, then everything will be lost. I mean, nothing can be calculated fast. Okay. So we define so psi dot AA is the, I think this stands for the amplitude at site J maybe, and so we declare that as ket, and we declare its conjugate as bra, and then we declare one observable, which is the zth component of the spin at that site. Sorry, and we take the inner product of this with, see, we declared the zth component of spin at that is our operator, this object, zth component of spin at site J, and we just calculate the expectation value in that state. This object, and we are just printing that out, that thing. what next few lines are doing.
So does he exhibit the matrix?
Matrix is not exhibited actually. No, we are not writing matrix at any point. What we are writing is we are actually expectation values of the 2s.
So that means we know that for spin 1 Heisenberg antiferromagnet, expectation value of SZ in the ground state is 0. Some kind of similar state. So if you start with a specific value of SZ, like upstream or downstream, then somehow it evolve to 0 value.
Okay.
Is that what is writing?
Okay, no, so I'll just run the program now.
Oh, so far it's a program, now it's going to be that.
Yeah, I have on the home page. This is on the website. Okay. This program is on the website. So this is actually the same program. So I've just copy pasted it here, and I've already compiled it. So let me just run it. Okay, so so initial energy we have printed, then largest m, so m is our parameter, during the sweep 1 was 9, and what happened there, energy truncation error was 10 power minus 6, 8 into 10 power minus 6. Eigenvalues at central bond are these values. Actually, this is just one number. So in descending order, we have written down the energy eigenvalues. Energy eigenvalues? No, density matrix eigenvalues, not energy eigenvalues. Yeah, density matrix eigenvalues. And the energy after sweep 1 is this value. So this was our random, no, not random state, the up-down state. Its energy was this. So after one sweep, we have got this energy. Then it takes the next sweep. So we are going to take 5 sweeps. In the next sweep, the m maximum value took was 16. It cannot go beyond 100, but it doesn't go beyond 17 actually in this simulation. Sorry. And again, there is some truncation error. Again, we have written down the eigenvalues of the density matrix in descending order. And in one step itself, it has sort of reached the. Maybe the initial condition of is special. I don't know.
Okay, so this is how the energy is reached.
Yeah.
Now we see also telling about SIZ as a function of position.
SIZ as a function of position. Yeah. So that's
a very important quantity.
Yeah. So
that was one of the primary reasons for Dmrg. I will comment on it.
So we have actually written 2 files. One of the file is this. This is the value of SZ
nice physics there.
at ith position. I don't know it is ith position or it is ith position because there are 100 lines here. Yeah. So I don't know what this is.
Did you want to say something?
I can plot it if you want.
I will come to the blackboard. Where do you plot it?
Okay.
Next please. With some amplitude, spin is up. So it is as if it is oscillating. Similarly, at this other end, you find. So, exactly, right. So, well, you going to explain this?
I don't know.
This is something beautiful. So, suppose you get a closed chain, there won't be any such oscillation. If you have an open chain, there is a quantum number fractionalization in this problem. In the sense, if you take the boundary and then integrate over the spin, you will get exactly spin half. So it is as if this spin 1 changes spin ones which are interacting with Heisenberg antiferromagnet manage to form singlet among themselves. But at the end, it leaves half of their spin. Half of a spin one is spin half. So half of another spin is spin half. So that's a beautiful example of.
So actually, write out the
Valence bond. So tomorrow, Dmrg will explain it in an extreme limit called Valence bond. Their basic idea is saying that you take a side and imagine it's made up of two spin half moments, and then a state like this corresponds to a case in which this quark of this quark is coupled to this quark and forms a singlet, and this is coupled to this and forms a singlet. So it's all happy, but when you come to the end, you find there is one uncoupled spin, so this is a spin half moment. So in the AKLT model, what you find is you have two loosely chain length very large. You have a free spin half moment here. You have a free spin half moment over here. Then when you move away from AKLT Hamiltonian and move to Heisenberg Hamiltonian, what happens is this spin half moment starts spreading, and that is what you see as an answer.
So that is an exponential thing with the gap.
Exactly. So if you extract a length scale from this exponential decay, you can convert it into a length scale, and that will be the gap of this particular number. So Dmrg became famous when they were able to evaluate this unpaired spin at the end very, very accurately. So this is very transparent in the AKLT model, which Dmrg will discuss tomorrow. Like there is one unpaired spin here and another unpaired spin. So this is a very nice example of quantum number fractionization, because you expect out of a spin system like this, excitations will have delta S is changing by one or spin one excitation. But here you have that, the spin of excitation at one corner and the spin of another.
So I get confused because there's also some Z2 symmetry that is broken, right? Yeah. Because you see
By hand.
By hand?
By hand. Because, in fact, yeah, this is a very important point. So if you are very careful, what happens, this spin off and this spin off will form a singlet, and it will be all disappear. So you have to apply a little bit of bias from the beginning, because we chose basis in which up, down, along this. So it's because of this initial choice. We would have chosen it to be in this direction, then it would be slightly different. So if you solve the problem exactly, it will be a total singlet. But then that's one component of a singlet will be one loose spin here, another loose spin, forming a very weak singlet. You can easily excite that, convert them into triplet state. Here we have biased it by the initial condition. And also this spin one model also contains something called topological model, which is also very clear in AKLT model, which Dmrg will explain.
So no, so that's all I think, and I think one more quantity was measured. So let me just check what that was.
So in a sense, now you measured it, right? You did the calculation.
Yeah, the simulation which ran just now. So this was the result of that. So H dot S was the other observable.
Bond energy. Spin. It's for the total.
So this is H dot S.
So that means.
Yeah, I think those. I think there is some font problem. Those boxes means minus sign.
Yeah. So this is also what happens if the spins in the middle of the chain are very happy. They are their spin objects are nicely bonded. But when you come to the boundary, there is a frustration.
It's also negative. It's actually it's also negative. I think that box.
Negative is fine.
H dot S is negative is fine. I don't know.
No. See, this mean value is.
Oh, so it is Si dot Sj. Sorry, Si dot Si plus 1. Oh, okay.
So it's not a universal number, because in the AKLT model it's a very simple number, whereas here it will be something different. But I see. So it's nice that the energy density also has oscillation in the okay.
So this, I think the point of this exercise was that this is a 2-point observable. SI, so you had to, in the calculation scheme, you had to put 2 red dots and then average over the rest of the things. Yeah. So the previous one was just a 1-point thing. So that was.
So we also, since you have done this, there is this topological order in this. Some operator, I don't know. It exhibits a long range order, which in fact later called topological order in other contexts. So this model is supposed to exhibit variance.
Okay.
Probably that can be also measured.
Maybe.
But it's very non-local object.
Okay.
It's not a 2-point function.
We take a topological order only in the sense that your perturbations they commute with this. They commute with this. You can't have any perturbations. So in one sense, it's
so that's a topological rigidity. So here, okay, let me. Can I have the lights? So there is a topological order in this state in the following sense. Let me. So if I take this wave function at this state and then project it to SZ basis, so a given site can have SZ equal to 0, plus 1 or minus 1. So these are all the 3 possible states. Now I open this wave function and then what I find is, according to, when you do this analysis, what you find is a sequence like this, plus 0, 0, 0, and then minus 0, plus 0, 0, 0, and so on. That is, amplitudes, the wave function that contribute to this final state, have non-zero amplitude only for configurations like this. So if you find me an upspin, there will be zeros, but you'll always find a downspin, never a plus. So if that intervenes, then this all order in the sequence will be lost. So here there is an order in the sequence, not in the position. So if there is a plus, it will be followed by minus, it will follow by plus, minus. So there is an operator which measures this. So this is the topological order content of the string multiplication.
The string operator.
It's a string operator, exactly. So since Ramshesha gave a clue, that's string operator. Yeah, I think it's some operator like this. I running between from. You take this SI between a point beside L and M, and then find the expectation value. It remains non-zero as L minus M.
sorry, but the concept of topological order,
Yeah.
we usually also demand that this quantity would be robust under the multiplication.
Correct, exactly. So this is exact. This can be exactly shown for AKT model, and then add to AKT model extra perturbation, which will make exactly like I said.
Right, but this perturbation has to be SU2.
Right.
Can't break the SU2.
That's right, exactly.
The symmetry protected topological order.
So the AKT Hamiltonian has some term like this. Whole square. So it has a standard Heisenberg topic and biquadratic topic.
Right.
So for a specific choice of A and B, that's AKT Hamiltonian, for which it's exact. Then you move away from a particular, you drop this, which is what he analyzed. Standard Heisenberg model. Still this topological order survives.
But you can't add a perturbation which does not compute with this.
Correct. You can't add like this magnetic field.
But usually, let's say if you talk about the tonic code or something, then you can add any local perturbation and then the answer is.
So this is also robust under some perturbation.
Right, that is all. And these are the perturbations which compute with the commute with the symmetry.
This is the expectation value of SI dot SI plus 1 becomes 1.
Yes, yes.
Now, if you had a spin half model, then you must have a pilot system, spin pilot system. So it should kind of give you an oscillation, short, long, short, long.
Yes, what happens is in spin-off model also there are these boundary spin-offs,
That's it.
but then they have power locking. It's not sharp like this.
It is very sharp.
Exactly.
So they should be able to see that.
Now, okay, there I think DMRG fails probably because of you need to have a lot of one dimension. Probably things like mere orbital.
No. Probably you can do a spin correlation function and then get the structure factor.
Mm-hmm.
You'll see the structure factor looking at 5 by 2.
Mm-hmm. But I do not know whether this method works for spin half. Whatever I have heard is that
Because spin one does not have a spin part system. There is only a spin half.
correct. But then at the same time it's gapless, so it's hard to. Maybe you can make. Suppose I force a DMRG calculation on spin half.
You would always see expansion.
There also.
So as you increase this parameter m, you will see that you get a larger spring, but
Still it will be exponential. Okay.
Firstly, if you take a square lattice and put spin 2,
Mm-hmm.
you get something like
Yes. So legs, some more legs. So I am preempting what Vidyaman will talk about. See, Jason has question, suppose I have spin 2 or I have a square lattice, can I do similar construction? The answer is yes. In the original AKMP paper also, AKMP is there. So think about spin 2 as made up of 4 spin half objects. Then you can say 4 quarks. So you can hook up a Hamiltonian for which this is an eigenstring. And so on. So similarly, if you have a honeycomb lattice, you can construct a spin 3 half because there are 3 neighbors. You can keep.
No, so then the question is, if I have a corner,
If you have,
a corner,
yes, will there be a trap? Yeah.
so there will be, no, there will be spin 1.
Depends on which corner, whether you have to look at the edge or you look at the corner. If you have a corner,
So if I have just an edge, then it will be a spin half.
exactly. So here it will be a,
Spin half. So if I have a corner, then I have a spin 1. Spin 1 there.
I do not know. Either spin 1 or spin 0. Because they may get paired.
Spin 0 also, yes.
They may also, right?
How can they get there? Because that particular side still has to be spin 2, so it does not have spin 1. Spin 1 cannot be there.
Okay. Very nice.
So there will be 3 states, three corner states corresponding to
Yeah, I think similar things will go. There are interesting surprises. You go to 3 dimension, like with 6 spin 3, you expect it to be a spin liquid. Then you find long range order. Even though you have written a wave function which looks like a singlet manifestly, but long range order develops and you get amplified. This is Parameshwar Shank, Parameshwar Siddharth and Shivaji Sondhi. Sumati, you had a question. Okay, great. So, please go ahead. You are. So, I think that's very nice. Thank you very much. It illustrates that iTensor can be used by us. Now I feel confident that go and look at the website. Okay. I think it would be interesting if we can solve another model which is not, which will give some new insight in the next 2 days and surprise Miles. Is there any, Rajiv, is there any discussion about Hubbard model in this iTensor site?
No, they have, Rajiv has to change the model here.
So this, the example which I gave today was available on the website itself. I didn't get time.
Oh, sure. And in the website, in the examples, do they have any other model like Hubbard model?
I don't think so.
Okay.
I can check.
I think you have
Okay, I see. That would be nice if some other models are there.
I think many models are implemented, but the documentation is not there. The
Okay.
documentation is not very detailed right now.
Okay.
So,
So Ramsesha, do you have any comments about this? Because you have played with spin chains also, right?
Basically, that's what it is.
So did you also focus on the edges and saw this unpaired spin at the edge?
No, actually, what we were doing was very different. In the
Ah.
sense that we were trying to get the structure factors.
Okay.
So for that, we do a calculation for about, say, 200 site.
Do Fourier transform.
Fourier transform the open chain.
Mm.
So what you do is you take, give out 20 boundary spins on each side. What you have in the interior, 160 sides. You assume that the spin coordination functions are that of a ring.
Mhm.
And then you use the spin coordination function in the ring of 160 to Fourier transform. And then you can see what happens to the instant.
I see. So for you it was a nuisance, the boundary oscillation.
I mean, it's been half.
Yeah. Let's see. So the another thing I was thinking was to go to Miles' lecture and clarify that point. Shall we do that? Do you have energy? Okay, maybe with that we can close. So that will be. That's all.
You may be able to just mount the Windows partition. You didn't have to shut that down. You could have mounted the Windows
Actually, I
partition.
have the presentation in the memory stick also. Yeah. So there was a comment made by Professor Balachandran about some connection to lattice gauge theory. Ball is not on. Did any of you appreciate that point?
I don't know. I got a sense that he was worried about some gauge symmetry.
Right. But then he also alluded at the beginning, it looks like lattice gauge theory.
That part,
Okay.
yeah. So no, I'm trying to connect to that.
Mhm.
So see the states S1, S2, S3, Sn, right? You can do gauge transformations on those guys. So for example, I can multiply each of the S1s by something, right? If that is a trivial thing to do is to multiply each by some phase. So then these wave functions will change. But if those fellows have internal, if S1 is n-dimensional, I can actually multiply this by SUN
Matrices.
centered around the ith side. So there is some, so I think he was worried about that. And another comment which said that this is actually written in a particular basis, in the sense that you fix the gauge of those, that internal gauge has been fixed. And that, I think.
So Sukhwinder, would you like to make some comment? Because you have worried about
Right. So,
incorporating local symmetries or global symmetries.
right. So,
Yeah.
so there are two things here. So one is
The rate what?
so one is your net body wave function, and the other is we are just using a representation for this. So I think what you were just saying, and what he was just saying was that, so there are two things. This is a wave function, and this is how we're choosing to represent this. And suppose I have one given representation. I can always, on this bonds, introduce a resolution of identity of bonds. Right? So x inverse, and maybe y inverse, and so on. And let's say multiply y and x inverse with the square, which is so on. Okay. A new and PS representation for the same state. Right? So there's a
HQM and choosing the representation for the wave function. But in lattice scheme, in a lattice gauge theory, we actually talking about the gauge symmetry of the wave function. So if I have some group and I'm actually transforming these groups to indices now.
Yeah, this is our.
Notice that over here the gauge transformation is in internal indices. So I'm demanding that if I act by some rule elements here, then this guy remains and this guy remains invisible. So that is the gauge symmetry of the wave function. This is just choice of some gauge for the representation.
This actually brings to another very important question. Do these dummy variables which you are integrating over, what do they mean? So they carry any physical meaning more than
right. So the syntax over here, the states over here are basically they give the states over here form a basis in the inverse space, which is the support of the reduced density matrix of all the cells to that effect. So let's say this label it takes 1 to n values. So this labels some m states, and those states will span subspace on which this side of the chain is supported. So it's an effective description of the left part of the system.
the basis for the
Yes.
class?
But there's a distinction over here. So these gauge transformations are just for your representation, and then this. Now on top of this, you can have a gauge symmetry for every function. And in fact, people have then translated or incorporated such constraints into the tensors of the MPs. But that requires doing something more. So you impose some gauge constraints for the tensors, special ones, all of this. So you still fix this gauge, but then you now impose some constraints of arising from such a gauge.
So maybe we will close with so let me go to the section where there was question asked by remember where it was.
I think you need to keep going down.
Going down.
Yeah. Right. Yeah. Okay. Keep going. Next. Yeah. This is the starting point.
Yeah. Well,
Yeah.
I keep going down.
Yeah. Right. This is the.
Okay. So now you and Ramsesha are going to speak and explain this to us.
Yeah. I think Ramsesha will go with experience.
No, all the three of you. So, yeah, I lost my, somewhere I came here, somewhere here. I was asking the question about this Hamilton. So, might give some answer. I didn't understand. Maybe, can you explain what is this Hamilton?
So since I'm new to this, I can try so that I learn from the mistakes I make.
Why don't you go there so that you can actually handle that?
Yeah. So the way I understood it is the following.
Yes. Please.
So the way I understood it is, so this was this side 3 we have. So let me just call this these fellows as alpha. Okay, why not use actually Ramsesha as 3? Let me call this as mu, and let me call this as mu prime, and this I will call as
Then the right will come.
So if I were to think of this as a 5-side problem, 1, 2, 3, 4, and 5. Basically, these mu's are the sort of the eigenvectors of the density matrix of these guys, and the mu primes, and mu's are these of this side. And now the Hamiltonian is written in this case.
So it may not have a particularly simple form.
Yeah.
So the form would depend on these things.
But if the interaction is somewhat local, for example, I was trying to visualize in terms of free particles, then what would happen is I would basically have a system like this, where this is my mu block, this I will call it as the mu block of the Hamiltonian, and this will be the, why did I get one?
There cannot be a mu block, it's called a mu block. Why cannot? Mu is for the left. See, mu sigma mu prime is for the raw vector.
No, mu block means this thing. Mu A.
You mean mu.
Not
Okay,
the
like mu. Yeah, sorry. Yeah, that's what I meant. And then there's the three block. That is the, and then
sigma 3 tau.
sigma 3 tau 3 block. Okay, sigma 3 tau 3 block. And then there is the mu prime block. Right now, I think for some simple Hamiltonians, what would happen is that you would of course have some terms here and some terms here. And I think what will happen is that you will get only terms here and here. So for example, this will be completely zero. Is that correct? So the left will not couple directly to the right. It will only couple through S3.
But even when you are not even sure that that form, I don't know which conditions you get that.
It will be all coupled.
Depending upon the number of particles on the left and the right side, if you are looking at a Howard Hamiltonian.
But let's just look at Heisenberg Hamiltonian.
Okay, Heisenberg Hamiltonian also different MS values you have for MS of U, MS of U prime, and then MS3. Okay, so
there
you
will
can
be
calculate
various
everything depending on what values MS3 can be.
So what this being stated is about it. So for example, so if I look at MS equal to 0, I could have, so this is my mu block, this is the 3 block, and this is the mu prime block. So I could have, say, up, down, up, or I could have, this is for MS equal to half. I could have up, down, up, or I could have down, up, up. All these various guys will couple together, and then the matrix will be full, is what you're saying.
Matrix may not be full, but
Yeah,
it
it
should
will
be
be
random.
You cannot have some nice structure the way I'm thinking.
Then what is special about this basis given solution? Leave some signature.
Okay. So now my understanding. So here is where I think we can help this up. So my understanding is that suppose you start with some set of matrices like this. This is the initial product state. And then the way to improve it is by this sweep.
Shifting side 3 to side 4, and then the rest of it you want to do is side 4.
And then keep doing this. That's the sweeping.
That's the sweeping vector.
So in a sense that
Sweeping statement.
Now, if you go to the sweeping, you will see that.
yeah.
Oh, let me.
What was it for this one?
We are going to
answer the last
Okay. Yeah.
This is a sweeping text.
Operationally, how does one do it?
It's precisely by what I would think precisely as demonstration. So what you do is you would say, imagine that
You keep changing the size of the left and the right one. Left block augmented, right block attenuated.
so let me say I have 2 n sides. So let me say I have n here, and so let me say n minus 2, and this is 2. right? I'm simply now I know some states mu here, and I know some states mu prime here, and then I have the internal states of this. So let me just call them as S. I think we call them as
Sigma.
So what I then do is I construct my Hamiltonian with this basis, diagonalize it, get my ground state. And then what I do is I compute the density matrix of this guy.
No, one side.
One shifted up, right?
Yeah, mu and sigma will be together, and then
I got it. So, mu and sigma together and this guy.
and no, you don't do anything to that, so that it becomes m plus 1.
Correct. This becomes n plus 1.
And
then
now
I take these two sides
Yeah, you put another side on the right,
on the right.
and then you look at the density matrix for n minus n minus 3.
Okay, n minus.
Because that was already computed.
Yeah, right. Correct. Right, and this goes on.
This goes on until you hit the right side, which is only one side, and then the left side will be n minus 3 sides, and middle 2 sides. And then now you sweep back. So that right side now becomes 2 sides, and then 2 new sides, and then n minus 4 sides. Like that. So now we have the new density matrix for row 2.
Correct. So the question is, why does this converge?
Huh?
Why does this converge?
Because finally these density matrices have to be density matrices of the full system, the 2n system. What you started with was not the density matrix of the 2n system. It was density matrix of the 2p system where rho p was from the 2p side system.
No, you made a statement that finally it has to be the density matrix of the 2n system.
Okay.
So what in this business is forcing that it has to be?
Because you are constructing back and forth, you are sweeping it, so it will finally become that of the, you are refining the density matrix until it becomes the density matrix of the 2n system only. Because you are starting from the 2n state, 2n side eigen state,
I see.
so that becomes a part of the 2n state density.
And you always have your Hamiltonian.
But when I started with the central, when you
You have to get the state and then only that state that is.
So keeping the Hamiltonian at each point and extracting the ground state.
On the same Hamiltonian. On the same Hamiltonian.
So suppose I want to ask you a different question. So if you look at Green's function Monte Carlo, the usual Green's function Monte Carlo, I would start. This is what you showed as e to the minus I. Right. So I would start with some state of this some state, and then I would just do e to the minus some tau p, tau h, and keep doing this, and eventually I will go to the ground state. Right? So what is the connection of that and the sweeping business?
There's two different ways of getting the same ground state.
Yeah, there's simply getting equal. So there's some.
They are numerically different techniques. Numerically, one is a projection operator and the other is a density.
Correct.
E to the minus tau h is a projection operator.
Correct. Does that help? It helped me a little bit, but yeah.
So, Shankar, you want to say something about questions that were asked? Let me ask the audience. What is the next question? So the question is, it's 5 o'clock. So we had a long day. What kind of models can be?
Typically, where can we use?
So, as I think Sukhvinder and also Mike said that whenever the system is a good gap, it is excellent, like AKT model, one-dimensional Heisenberg spin chain, and Hubbard model at half filling, where you have a charge gap.
2D has been used.
2D, I think that's where the frustration is. You cannot enlarge it because if you literally enlarge it, the computation time becomes
You can do it for thin strips. I think people have done it for about, this thing, 10-leg ladder. About 10-leg ladder is about the widest system that we have on.
So you still try to mimic it one dimensional, but then have a finite breadth in one direction, and then keep increasing it. people have done it for the Kagome lattice spin problem, and also in TJ model and various things. And there are problems. For example, there is one method called IPEPS which has been used to analyze TJ model, and it amplifies like stripe instability enormously. It gives you a very large charge order. There was a nice comment from Sandro Saramose. In fact, if you do it properly, it should not be there. So when it comes to two-dimension, I think you can tell me. There has been ideas like even this Mera is suited to two-dimensional gapless system. Then when it comes to spins and charge degree of freedom behaving differently, the structure of Mera has to be different. So there are ideas and preliminary works.
Can I just ask the question in a different way?
Yes.
So this entire tensor network game, what problem has it solved, or what new insight has it given on any problem for which we did not have any insight before?
So I think like last one was saying, so these methods have recently started, people have recently started using them for actually hard problems. So before this we were just using some confidence building. The Dmrg have been used for the last
I think the way I have understood is tensor networks allows you to go to higher dimensions conceptually in a framework which is very similar to the
but it's just generalization of it.
So basically that's the point.
So like two dimensions, if you have the ferromagnetic on a Kagome lattice.
So you will have a mu left, mu right, mu top, mu bottom, and then a spin sticking out. And then now you trace over the left, right, top, and bottom, then you will get the matrix product state corresponding to the two-dimensional network. And similarly, you can do the three-dimensional network. So the point is that conceptually it is easy to extend it to higher dimensions.
But what have we learned new? That's what he is asking.
Because I was saying that there's this.
So actually, I think what have we learned is not the right question to ask, because then there's nothing for us to do. Where is it possible?
Where is it?
I mean, what directions are possible?
Possible, right?
To get to this? Because if it's already a done problem, then you know.
So to me, now to answer this question, this ADS-CFT correspondent always was mysterious to me, continues to be mysterious.
Can you please expand ADS?
Anti-de Sitter space and conformal field theory correspondence. Apparently, if you look at a three-dimensional quantum field theory, gapless, if you look closely, you see a one extra dimensional gravity world. So a D plus one dimension, and we're using things are simpler in that world, and you can compute strong coupling quantities. This is what people say. But when this involves a lot of mathematics and a lot of jargon, I never understood it. But when I read this Mera answers, in some detail, it was very beautiful that you could see there is a renormalization scale and the scale structure. So that was definitely new, which was not there in any variation of wave functions that I am familiar with. So that
I've seen people keep talking about central charge.
correct.
Okay, and then velocity or something like that. So they try to extract from the Dmrg wave functions of the models, these quantities.
Right.
They are apparently
Very
conformity.
So this is in 1 plus 1 dimension. Yeah, you want to
Right, I mean, you can compute a lot of formal data using either MPS or
What I don't know is I don't have the problem field.
Neither do I. But we have experts in math science. The next 2 days we can.
So on that point, is there a known problem for which there's some new insight has come out of this?
So the example I was again giving was the guitar model on this. I wouldn't say that new insight. I mean, this is just beginning to people to start using this to look seriously at these hard problems. But for example, for the guitar model, we can go up to 108 sites. 108 sites on the Kagome lattice. And before that, the best results were exact diagonalization for about.
So no, this is not detailed. This is Kagome lattice problem.
Yeah.
Yeah, right.
But J1, J2 is still.
J1, J2 still up. Okay, there are two family of problems. One is spin half Heisenberg model on a Kagome lattice. There are lots of results in the past. Some people say it corresponds to valence bond solid. Some people say it's a liquid. Now Dmrg made some contribution, and then this tensor network now seems to have converged something which was not possible before, saying that it's a spin liquid, numerically. Then recently there are attempts to understand, which is what Mitri will do tomorrow, so-called J1, J2 model. Square lattice competing interactions. There seems to be some spin liquid phase in many interesting things. So these were things that were not possible to address so accurately in the past.
No, but problem is debate. It's not like people are believing that result is correct.
Exactly. So it has started a debate. It has given a beautiful, perhaps controversial result. So people are challenging it. Because in that model there is a region where the two competing interactions fight, and some people thought that it should be a crystalline valence bond, solid phase. Recent research shows it's a liquid, and somebody has challenged it. So
no, Mera shows it's a liquid. I mean this tensor network.
Tensor network, not Mera.
Not Mera is critical.
Matrix product states are tensor network. Says that it's a liquid. And Sandvik has come up with some suggestions that we use. So it's interesting that but the energy differences are very, very tiny in all these things.
But we are people of Hubbard model. So what is doing this tensor product in Hubbard model?
We are preparing groundwork to conquer, Everest. We have to climb small nearby hills. That's what we have done. Now the question is, we are Hubbard model people. That's what Hassan says. We want to solve Hubbard model in two-dimensional PJ model and prove high temperature superconductivity. So at least that's my ultimate aim. Ulterior motive. But these are all definitely things to understand. And in fact, one of my aim was to talk about that, so-called Grassmann and tensor network states. Now I will not talk about it. Conveniently, I have fixed Amshisha's talk.
So can the correlated system be studied as a function of filling using Dmrg?
Yes, people, in fact, there is something called IPEPS, it's part of this tensor network progress, which they have studied TJ model and gotten some very exciting research in terms of energies. But in terms of physical properties like charge density, where there seems to be too much of density wave pattern, so that is under question. So it has been studied. Though TJ model has been studied in the last 1 or 2 years. Steve White and
1D or
2D TJ model. Very beautiful research. But then the research is very good. But when I looked at it, my immediate reaction was it cannot be right, because there are various reasons which tell you that you don't expect this much charge density modulation. And now it turns out to be so that it holds on to something and amplifies it. So that there are hopes for improvement. Shankar, you want to say?
So in 2D, even if the numerical calculations are difficult, is it possible to write down, say, treat it as variation wave function?
And some answers.
And try to write down correlated wave functions with fractional charges. And what I have in mind is analogy of Laplace wave function. Because those wave functions, even if you don't know plasma analogy and don't know how to calculate, you can nevertheless sort of motivate them fractional charges and very phase calculation and fractions. So has there been any attempt in those directions?
So unfortunately, when it comes to away from half-filling in a 2D PJ model, the best wave functions are RBB wave functions with pulsar projection characteristic by 5H.
Now what do you mean by best? I don't care about energy actually. I'm only worried about the topology.
Best so far it has been in terms of the desired result it gives, namely it gives superconductivity.
But I have
and also energy is good.
Yes, but
I have a
my
problem.
question is not towards superconductivity at all.
Yes.
My question is more spin liquid.
So you're talking about dope Hubbard model or?
No, I'm not. Spin models in 2D.
Oh, sorry, I'm sorry. I thought you were talking about. So you are not talking about doping.
No.
So spin model.
Yes.
Okay. So there has been attempt to understand triangular lattice. Unfortunately, it orders, so there is no spin liquid. So that is where this J1, J2 model and so carbon
what I'm
lattice.
saying is, energetics is difficult because you have to do the calculation.
So you are asking whether there are model wave functions, variational wave functions.
And showing topological order in them by tensor.
In fact, the whole class of work by Ben, what is called projective quantum PG something.
Yeah.
So he does RBB mean field theory and takes those
So
answers.
are those tensor network representations?
Yes. In fact, they are called Grassmann tensor. They are very nice developers. So you take those and analyze for this projective symmetry. And then that gives you what kind of topological order you will get after Brussels projection.
The spin model, where is it?
Spin model.
So Brussels projection.
No. You start with the spin model, do RBB mean field theory, where things are freely moving. And then get those mean field waveforms. Spin liquid waveform. And then do Brussels projection.
So where does tensor network come in?
So this can be rewritten in using Grassmann variables like a tensor network. That's called Grassmann tensor networks. These are very recent developments. And, I think our next conference should be on fermionic tensor networks. So there are very exciting things going on. Unfortunately, we will not be able to touch upon.
So even the quantum double models, so these other models, so I think generalizations of the Turing code. So even they are the ground states of all quantum, or at least a very large class of quantum double models, can be written exactly as if they are the ground states of this.
2D models.
Yeah.
So the TJ model, suppose we set the J equal to 0 and U equal to infinity, the so-called extremely correlated liquid. Has there been any
Tensor network operation, not as per se. It will be very interesting. So there is a lot of scope within spin models and globe spin models. I think it's all just the beginning as far as I can see. And also I should say that most of the approaches are very numerically based. There is a beautiful structure behind, but at the end you have to use computers in a very powerful way to extract results. Whereas in the slightly modern times you can write down a RGB wave function and then get away by hand-waving arguments and doing some heuristic. Now you can't get away with it. You have to go to high tensor. Okay, I think we had a very good time today. So I hope you all enjoyed it. So enjoy the rest of the evening. But please remember to solve one problem tonight and then. We'll meet tomorrow at 9:30 sharp. The first talk will be by Miles Schoenmeyer. So we will meet you tomorrow. I think dinner will be served in the same place.